Before we begin, let's play Mafia game. Suppose there are 4 players playing the game, 1 Mafia and the rest being the citizens. The goal of this game is to find out who the Mafia is. Now, from the perspective of how computers deals with this game, we can simplify the problem by thinking the citizens as the 0 bit and the Mafia being the 1 bit. Since there are 4 bits in total, we can store them in each of the 4 memory slots. Now we have 2 different computers that deals with such issue. Computer 1 is the classical computer and the other one is the quantum computer. The classical computers approach this problem algorithmically. So first, we pick a random number, check the memory slot and see if it's 1, and the step 3 is iterated until the memory slot finally contains bit 1. This entire process takes 2.5 turns on average. The second method uses the quantum computer, but surprisingly, such method only solves this problem in one shot. From this, we can easily realize that the 2 types of computers are fundamentally different. Now let's delve deeper into how quantum computers actually work. Remember that we use the term bit to represent each individual players of the Mafia game. The quantum computers use qubit, the quantum bit. Quantum bit is conceptually similar to bits, except that it contains the quantum information and behaves like an artificial atom. For example, we can think of qubit as one of the valence electrons of the phosphorus atom, which can be part of the p-type substrate in the NPN transistor. So all electrons have magnetic fields, so they're basically like tiny bar magnets, and this property is called spin, which line up with the magnetic field of the Earth. There is an up and down state, each representing 1 and 0, and 1 represents the highest energy state, and this is the lowest energy state. To differentiate the energy state of the electron when it is in up and down state, we need a strong magnetic field using superconducting magnet, which is a coil of superconducting wires. The down state of the electron can be simply created by giving it the magnetic field that points downwards, and such state points to the down state, which represent the lowest energy state. On the other hand, creating an up state is a little bit more trickier since it requires microwave of specific frequency, just like how radio waves must be tuned to specific frequency to be heard. So what characteristics should a qubit exhibit? The atomic nature should first be discussed. Under the microwave tuned at specific transition frequency, the energy separation was not the same for every pair. Notice that the E1, E01, and E12 is different in this case. So this means that there will be no leakage in the system. In other words, the electron can be moved from 0 to 1 state, however, it cannot go further, for example, from 1 to 2 state. So this can be considered as a good 2-level atom approximation. So the artificial atoms in circuit can be demonstrated using this circuit here. And if we make the energy vs flux diagram through the equation E equals Q squared over 2C plus flux squared over 2L, then we can come up with this diagram with a parabolic shape. However, we can easily notice that the energy separation is the same everywhere. So once the voltage is applied through the voltage source, then the electron is moved from 0 to 1 state. However, there's nothing that prevents it from going further from 1 to 2, 2 to 3, and so on. So at the end, we end up with a superposition of so-called coherent state of all the possible states. This causes a major leakage, and this is not a qubit. So we need a nonlinear limit. We have one such element called Josephson junction. The basic structure has a very weakly coupled superconductors and a very thin insulating layers called Josephson junction. And the Josephson junction basically acts like a nonlinear inductor, and the reason for it will be explained further. The Josephson junction is a new device that defines a new computational system, and to make it a qubit, we need the second element, the capacitor, making the regular linear capacitor of superconducting material. And tying these two together with resonator, that can behave as a qubit if we tune the parameters right. So to make a useful qubit processor, we need to tie different qubits together. We can then use microwave to couple them and provide in and out resonator through the readout resonator. Taking a closer look, we can know that current will be able to flow in the insulating layer through the quantum tunneling because the two superconductors are placed in proximity. There will be a specific relationship between the current that flows through this sandwich of superconductors and the flux, which can be defined as the difference of voltage through the junction. So plugging the current equation here to the current flux relationship, we can come up with the Josephson induction using this equation. So this qubit behaves similar to the inductance by demonstrating the nonlinear function of the flux. And notice that the energy is proportional to 1 over L here, right? Now let's revisit the circuit. We should revise the circuit of an artificial atom by making sure that it resembles the actual atom. As aforementioned, energy is proportional to 1 over L, so instead of the parabolic potential, we now get a cosine potential because, as we derived before, inductance, the Josephson inductance, is proportional to 1 over cosine, and if we take an inverse of this, which is proportional to energy, then we should get a cosine curve here, as shown. So now, the levels are no longer going to the infinity as demonstrated by the parabolic potential, but goes up until a certain point as the cosine curve. Levels are readjusted so that the energy levels are not uniformly spread, which is basically what we wanted. Because the energy difference is different, there's no leakage, and that's, again, what we try to achieve. Lastly, let's talk about the Josephson energy. So the Cooper pairs would tunnel back and forth because of the tunneling effect, and the frequency of the tunneling is EJ. So this is the rate at which Cooper pairs are tunneling back and forth. The larger the EJ, the faster the Cooper pairs move. This energy equation can be demonstrated using this EJ variable, using the fact that E is the integral of Vt times It. And we can finally derive the equation that E equals negative Ej of the cosine function. Accordingly, we can readjust the Hamiltonian equation that H equals Q squared over 2C minus Ej times the cosine function. So in order to make a useful qubit processor, we need to tie these different qubits together using the microwave buses to couple them, and then finally provide the input and output through the readout resonators that then couple to the outside. This is how we make qubits.